Published research has documented a chimney system that ventilates and cools an entire home for a one-time material cost under $300. No compressor, no refrigerant, no electricity. The chimney stands between 10 and 20 feet tall. One shaft cools up to 500 square feet. The interior air temperature drops by 5 to 15 degrees Celsius depending on design and climate. The concept behind it is more than 3,000 years old. Some versions of this design are still standing after more than 5 centuries of continuous use. The operating cost is $0 per year for the life of the structure. 88% of American homes now run on electric air conditioning. Almost none of them use this. This is called a solar chimney. And this is the story of the Persian architects who mastered passive cooling before the Roman Empire existed, the physics that turns a dark shaft into a zero-energy ventilation engine, and why the modern building code was never written to accommodate it. To understand the solar chimney, you have to go back more than 3,000 years to the sun-scorched plateaus of ancient Persia. In cities like Yazd, in what is now central Iran, summer temperatures routinely climb past 50 degrees Celsius, 122 degrees Fahrenheit. The air is bone dry. For the people who built their lives in that landscape, cooling was not a matter of comfort, it was a matter of survival. They did not have electricity, refrigerants, or mechanical fans. What they had was an intimate mathematical understanding of how air behaves when it changes temperature. Persian architects designed tall, chimney-like towers called bâdgir, a word that translates literally to windcatcher. These structures rose from the rooftops of mud brick homes, some reaching heights of 30 meters. The tallest surviving bâdgir stands in the Dawlatabad garden in Yazd at 33 meters, nearly 100 feet. Inside, the towers were divided by vertical partitions into multiple channels, catching wind from several directions simultaneously and forcing it downward into the living spaces below. In many homes, the incoming air was routed through underground water channels called qanat, where evaporation cooled it further, by as much as 10 degrees Celsius, before it reached the occupied rooms. No fuel, no moving parts. The entire system was built from local mud brick and timber. UNESCO recognized Yazd as a World Heritage Site in 2017, describing the city as a living testimony to the intelligent use of limited resources for survival in the desert. But in 1982, German civil engineer Jörg Schleich built the world's first prototype solar chimney in Manzanares, Spain, a tower 195 meters tall that generated electricity from nothing but heated air rising through a vertical shaft, and it ran continuously for 7 years. The solar chimney works on a principle called the stack effect. When sunlight strikes the exterior surface of a dark, vertically oriented shaft, the air trapped inside absorbs heat through convection and radiation. As that air heats up, its molecules spread apart. The heated air becomes less dense than the surrounding atmosphere. And less dense air does only one thing. It rises. As the warm air climbs and exits through the top of the chimney, it creates a pressure drop at the base. That negative pressure pulls cooler outside air into the building through ground-level openings, windows, vents, or purpose-built inlets positioned on the shaded side of the structure. The hotter the chimney surface gets, the greater the pressure differential. The greater the differential, the faster the airflow. The physics are governed by a simple relationship. Airflow velocity increases with both the height of the chimney and the temperature difference between the air inside it and the air outside. A temperature differential of 20 degrees Celsius across a 3-meter shaft can produce air velocities exceeding 1 meter per second, enough to ventilate a standard bedroom. On a clear summer afternoon, a well-designed residential solar chimney can sustain 8 to 15 air changes per hour in the connected space. ASHRAE standard 62.1 sets the minimum at roughly half an air change per hour. A solar chimney delivers 10 to 30 times that with no fan and no electricity. Think of it as a pump with no moving parts. The sun is the motor. The chimney is the pipe. Gravity and thermal buoyancy do the rest. The construction is deceptively simple. The south-facing wall of the chimney is glazed with glass or clear polycarbonate to allow solar radiation in. The interior surface opposite the glazing is painted matte black or lined with a dark, high thermal mass material to absorb and re-radiate heat into the air channel. The remaining sides are insulated to prevent heat loss. The result is a confined vertical column that functions simultaneously as a solar collector and an exhaust flue. But what happens when the sun goes down? In a purely solar-driven chimney, airflow diminishes after sunset. Designers compensate by building thermal mass into the chimney walls, concrete, stone, or water-filled containers that absorb excess heat during the day and release it slowly through the evening, maintaining a reduced but measurable updraft for several hours after dark. In arid climates, where the diurnal temperature swing routinely exceeds 30 degrees Fahrenheit, the night air entering through ground-level inlets is naturally far cooler than the daytime peak. Even modest nighttime airflow delivers meaningful cooling. Heat rises, cool air follows. The chimney does nothing but let it. And the performance of these systems is not anecdotal. It is backed by decades of documented research. Researchers at the University of Mérida in Mexico assessed a rooftop solar chimney attached to a single ventilated room under both summer and winter conditions. The chimney improved natural ventilation rates by 8 to 45% during summer, compared to the same room without one. Both configurations met the minimum air exchange requirements of ASHRAE Standard 62.1. In a separate study focused on hot climate performance, a solar chimney paired with a windcatcher and a water spray system was tested in a 2-story building. The integrated system achieved an average indoor temperature reduction of 5.2 degrees Celsius during peak summer hours and generated approximately 9 air changes per hour. It reduced energy consumption for ventilation by 90% and cooling energy by 75% compared to a conventional mechanical baseline. The most striking result came in 2001, when Raman and colleagues tested a solar chimney connected to a roof duct lined with evaporative cooling media in northern India. The outdoor temperature climbed to 43 degrees Celsius, 109 degrees Fahrenheit. The room temperature held at a near constant 28 degrees Celsius, 82 degrees Fahrenheit. A 15-degree drop, no compressor, no electricity, no refrigerant. Now, compare that to the conventional alternative. A central air conditioning system costs between $5,000 and $12,000 to install in a typical American home. It requires annual professional maintenance of $150 to $300. It lasts 15 to 20 years before full replacement. The U.S. Department of Energy reports that air conditioning accounts for about 12% of total household energy expenditures, roughly $265 per year on average. Over 20 years, the total cost of ownership, installation, energy, maintenance, and repairs exceeds $15,000. A solar chimney can be built for under $300 in materials. It has no compressor to fail, no refrigerant to recharge, and no annual energy bill. And the cost gap between those two systems is enormous. So why is the solar chimney not standard in new American homes? The answer lies in a regulatory and financial system that was never designed to accommodate passive ventilation. The modern American building code is written around one foundational assumption: that indoor comfort and air quality require mechanical systems. ASHRAE Standard 62.2, the residential ventilation standard adopted across most jurisdictions in the United States, mandates whole-house mechanical ventilation in all new construction. The International Energy Conservation Code reinforces this by requiring tightly sealed building envelopes paired with mandatory fan-driven ventilation systems to compensate. The logic is internally consistent: seal the building envelope, then mechanically control the air exchange. But the practical consequence is that a builder who wants to use a passive solar chimney as the primary ventilation strategy has no clear compliance pathway under the code. No section of the International Residential Code addresses solar chimneys by name. There is no prescriptive standard, no tested performance metric, and no recognized category for a passive stack ventilation device in residential construction. An engineer can model the airflow, demonstrate that it meets or exceeds the required air changes per hour, and still face a building inspector who has no checkbox for it on the permit form. The solar chimney is not explicitly banned. It is simply unrecognized. And in building regulation, unrecognized functions identically to prohibited. The HVAC industry reinforces this gap. Residential air conditioning in the United States represents a market worth over $29 billion per year. That figure includes equipment manufacturing, installation labor, refrigerant supply, ductwork, and annual servicing. The average American homeowner will purchase 2 to 3 complete air conditioning systems over the lifetime of a single house. Each installation generates revenue for the manufacturer, the contractor, and the utility company that supplies the electricity to run it. A passive chimney that costs $300, never breaks down, and eliminates the need for a compressor is not a product that market has any financial incentive to promote. Mortgage appraisers add a final layer of friction. A home without a conventional HVAC system will, in most American markets, appraise lower than an identical home with central air, regardless of whether the passive system performs better. Lenders require the appraised value to justify the loan. If the appraisal drops because the home lacks a recognized cooling system, the buyer either covers the gap in cash or loses the deal entirely. The financial system penalizes the homeowner who chooses the cheaper, longer-lasting, zero-energy alternative. No one sat in a room and decided to bury the solar chimney. The building code was written for mechanical systems. The financing system was built around mechanical systems. The contractor workforce was trained exclusively on mechanical systems. And the passive alternative, the one that costs less, lasts longer, and runs on nothing, was simply never given a seat at the table. It was set aside not because it failed, but because the system was never designed to accommodate it. If you want to integrate a solar chimney into your own home, here is what that looks like in practice. There are 2 primary paths: a retrofit to an existing structure and a built-in system for new construction. For an existing home, the most practical approach is a wall-mounted solar chimney attached to the south-facing exterior. The structure requires a vertical shaft between 8 and 15 feet tall, with an air gap of 3 to 6 inches between the glazing and the absorber surface. The sun-facing side is glazed with 6mm twin-wall polycarbonate sheeting at approximately $2 to $4 per square foot. The interior absorber surface is painted with flat black high-heat paint. A single quart at roughly $10 covers the entire interior of a residential-scale unit. The remaining sides are insulated with rigid foam board, typically 1.5 to 2 inches of extruded polystyrene at about $1 per square foot. The frame is built from pressure-treated 2x4s or 2x6s. At the base, a vent opening connects the chimney to the home interior. At the top, a weather cap with a screened outlet allows heated air to escape while keeping out rain and debris. For a chimney serving a room of approximately 500 square feet, the total material cost sits between $150 and $300. Build time is a single weekend. For new construction, the professional approach is to integrate the chimney into the south-facing wall from the design stage. A masonry solar chimney with thermal mass in the absorber wall and a glazed air channel can be paired with buried earth tubes, 4 to 6 inch PVC or HDPE pipe, laid 4 to 6 feet below grade and running 40 to 100 feet in length before entering the building at floor level. At that depth, the soil temperature across most of the continental United States holds steady near 55 degrees Fahrenheit year-round. Air drawn through those tubes arrives pre-cooled by 10 to 20 degrees Fahrenheit before it ever enters the living space. The combined installation cost for a solar chimney and earth tube system in new construction ranges from $800 to $2,000, a fraction of the $5,000 to $12,000 required for conventional central air. And if you want to push the system further, you pair the chimney and earth tubes with thermal mass flooring, polished concrete, or stone tile over a slab-on-grade foundation. The floor absorbs the cooled air temperature overnight and releases it slowly through the afternoon. The result is a home that maintains comfortable indoor temperatures through the peak of summer with zero operating cost. The maintenance is the final piece of the puzzle. A solar chimney has no filters to replace, no compressor to service, no fan motor to lubricate, and no refrigerant charge to monitor. An annual visual inspection of the glazing seals and a wipe down of the vent screens is the only requirement. The solar chimney is a 3,000-year-old answer to a 21st century problem. It costs under $300, consumes zero electricity, and delivers measured temperature reductions of 5 to 15 degrees Celsius in published research. Year after year, with no energy bill and no service contract. A lot of what this channel covers runs outside the conventional norm, not because it doesn't work, but because the system was never designed to accommodate it. If rediscovering this kind of knowledge matters to you, subscribing and sharing is the simplest way to make sure it keeps being found. And if you want to see a $50 system that heats your home forever and eliminates your energy bill entirely, that video is up next.